organizing this workshop and inviting me. So you probably remember I was giving the lecture on Markov chains, and so, I mean, as I take the, I mean, I was not sure what we will be doing in this panel discussion, but so far it has went well. But what I would like to hear from you, do you have any question about what I have discussed last time? If there is anybody who wants to ask something about what I have talked about, let's take those questions first. If not, then we will have some open discussion. Anybody has any question about what I talked about last time? Okay. So then you have any question about any of the lectures that you would like to address me? I may not be able to answer that, but is there any general query that you have about different topics that have been discussed and you want me to address that? Which of these talks confused you most? You have any, but it may not be the entire talk. Anything that one of the speakers has said, something that has confused you, you may start from there. Anyone has some confusion about something that, yes?
Please feel free to answer.
So nobody is confused about anything. It can't be. Then the workshop is a complete failure. If nobody is, yes?
I would like to emphasize one thing, that without taking this microphone, don't ask any question or anything, because we need your feedback. And if you don't take this microphone, it may not be recorded properly.
Okay, yes.
This, I heard so many things about this MCMC technique, and you also gave very good presentation on that. But I have one problem, that I need some books or something that can go like problem oriented. Like every time I start reading that MCMC or Markov chain, they will start from some integration and all, and I stuck somewhere and I will.
But let me ask you a question first. Okay, so what is the reason for your interest in MCMC? Are you working on some problem where you need MCMC, or you want to do your research on MCMC? I mean, what is exactly the reason you are interested in MCMC?
No,
are you a PhD student?
Yes.
Yeah. So what are you working on?
I am working on cure rate model,
Okay.
cure rate survival analysis. Cure
Okay.
rate model.
Now, why are you concerned about MCMC?
Sir, because everybody is talking about this Bayesian things and all, so I think that I should also try.
Okay.
Because I went for some PhD.
So then your interest, I presume, in MCMC is for the sake of learning about MCMC, okay?
Yes.
And if that is the reason, then you can't avoid learning a bit of basics and bit of theory, right? Okay. Now, if you have a problem where you want to use MCMC for solving one of your problem, that's a different thing, okay? But so tell me which one you want me to address. Okay, so suppose do you have, like, you have a Bayesian problem and you want to compute something and you need MCMC for that, then I can tell you something about
today, one that professor sir gave example of that he drawn some diagram and that kind of stuff. Suddenly he came to the conclusion like this is Metropolis Hastings. So I never knew that this is Metropolis Hastings, because I read something, but I don't remember.
I also mentioned about Metropolis Hastings in my lecture. Okay, no. So where were they told about Metropolis Hastings today?
Professor Arnav Chakraborty was talking about some.
But I thought was he talking about Markov chain Monte Carlo, or?
Yes, he talked about Markov chain Monte Carlo in his first lecture.
So he drawn some network, and it was.
So he was probably giving a specialized version of Metropolis Hastings. Is that correct? Yeah. Okay. Okay. So. I mean, see, this Metropolis Hastings, why it is so famous, let me tell you. Okay, maybe I can write something and then I can give you the crux of Metropolis Hastings, okay? So, see, the problem sort of starts from here. Okay. Say I have let's say I have a probability mass function or a density function. I will take a mass function, and suppose your probability distribution is on a finite set. Then it's easier for me to explain. I mean, things are easily generalizable if you have a continuous distribution with a PDF and such things. But for the sake of explanation, I'll just take a simple situation where you have a probability mass function supported on finitely many points. Okay? So let's say this mass function fx, this is like some constant times some function fx, and this x takes values in some finite set. Last time I was writing something like a probably, I don't remember. Okay? Suppose I have a very nice formula for fx. Okay? For example, let's take the Poisson distribution. It is e to the power minus lambda, lambda to the power x, x factorial. Okay? Now, suppose you haven't learned enough calculus to know what is e to the power minus lambda is. Okay? But you have learned enough algebra to know what is this, right? E to the power minus lambda is something that you learn when you learn a bit more on calculus, right? So, for me, I write this as some c, because I don't know what is that constant e to the power minus lambda is. Okay? So, this is my fx. So, many times what will happen, you might have, like in Bayesian inference, you know, you have to calculate the posterior. Okay? So, you have a prior, let's say this is your likelihood, this is the prior, and this is the posterior, right? Okay. Now, quite often what happens in Bayesian analysis, it is very difficult to calculate this integral. Okay. And most of the time, you don't have a nice formula for this. So, if you have some special distributions and special priors like conjugate priors, then it is very easy. Like normal distribution with normal prior, then you can calculate such things. Okay. But it's not very difficult to calculate this numerator. The problem is with the denominator. Okay. Like this you can think of like a denominator. Remember when I had this Gibbs distribution, I had a big sum in the denominator. Okay, what was the Gibbs distribution that I was writing? The Gibbs distribution was this thing, something like this, right? Beta. This is what I was writing when I was lecturing on 5th. Okay. The biggest challenge was to calculate this, and we wanted to avoid that. That was the sole purpose of Metropolis Hastings. It's like I know the probability density function or probability mass function up to a constant multiple, and that constant is something difficult to calculate. Okay? Metropolis Hastings gives you a way of generating data from the distribution even if you don't know that constant. That is the sole purpose of this algorithm, so that you can avoid such things, this big sum or this integral. You only know the numerator, but you can generate from the corresponding distribution. See, the numerator is not a probability density function or mass function unless you have the denominator there, right? Because it will not integrate to 1 or it will not sum to 1. Remember what I was doing for Metropolis Hastings? I was taking an x by some arbitrary distribution. I was randomly generating an x. Then I was randomly generating another x. Then I was comparing the value of h at the two generated x, and then I was doing something. And that does not require knowing this denominator. That's the beauty of the algorithm. So this algorithm is so famous because it does not require you compute something that's very difficult to compute, still gives you a way of generating from that distribution. It's like you are generating from a probability distribution without having the normalization. Okay? That's the whole purpose of Metropolis Hastings, and that is why it was a great breakthrough. They could identify a Markov chain with that distribution as the stationary distribution. That was the discovery. They could identify a simple Markov chain from which you can generate sequentially, for which the limiting distribution is that. So now you understand why Metropolis Hastings. Okay, it's all to avoid calculating that normalizing thing. Okay, so Bayesians like that because Bayesians, when they have a complicated prior distribution or a complicated likelihood, they have difficulty computing this denominator. Okay, but it's easy for them to get that, and it is enough to generate from this distribution by Metropolis Hastings if you just know the numerator. You don't need the denominator. So now you understand why Bayesians are talking about MCMC all the time, because they have a hard time calculating this integral. That's the whole purpose. Okay, so what they will do, they want to generate from the posterior. For example, suppose they want to calculate the posterior mean, which is the Bayes estimate. What they will do, they will generate observations using Markov chain Monte Carlo. They will generate a lot of observations and then they will take the average. That will be their estimate. That will be their posterior mean. Okay, that's the sole purpose. So in some sense, it's a computing device that helps you to evaluate the posterior distribution without normalization. Okay? Okay. Yes?
So, does Newton-Raphson method do the same thing?
No.
Like Metropolis Hastings algorithm?
No. Metropolis Hastings is an algorithm for generating something from a probability distribution. Newton-Raphson is a way of solving an equation numerically. The two problems are different. They are not algorithms for same problem.
Like in Bayesian, when we say that we are using MCMC technique,
Yes.
and we always use that MH algorithm to generate sample from the posterior distribution.
Yes, the Metropolis Hastings algorithm. Yes.
Yes.
But where from, I don't see where from Newton-Raphson is coming. Newton-Raphson is a procedure or an algorithm for computing solutions of an equation. Here we are not computing solutions of an equation.
We are just generating sample.
We are generating sample from a posterior
Posterior
distribution. Okay. Both are iterative and both generate a sequence, but they are for different purposes. They are not for the same purpose. Okay. Yes.